Hey guys, this is part of our series on 9 techniques for rewriting integrands so that our basic rules will apply. And this is our third technique. It's called completing the square. Here's an example problem where you might want to complete the square. First thing I do is I look at it and I ask myself if any of my basic rules will apply. It doesn't look like any of my basic rules. The closest one that I have to it is the Arc Secant Rule. So we got a rule that looks like this. The integral of 1 over x times the square root of x squared minus a squared. We know from what we studied in Calculus 1 that the antiderivative of this is 1 over a times arc secant of the absolute value of x divided by a plus c. This looks very similar to this. But here's an x minus 4, and that just has an x. And this one has an x squared, which is good, but this is not just a constant. That a squared could just be any constant. I've got an 8x. The fact that there is an x here makes me think I probably want to complete this square. So we're going to use this technique when, or I'd recommend that you use this technique when your integrand involves an x squared plus bx. And again, in this particular case, this looks a lot like an arc secant. It's not an arc secant. So I'm probably going to complete the square, and then after completing the square and doing a u sub, this is probably going to be an arc secant after the u sub. So keep that in mind. I'm seeing the x squared plus bx, or x squared minus bx in here, and that tells me I probably want to use this technique. But in particular, we tend to see this technique used with integrals that eventually become one of our inverse trig functions. So I'm looking at this and I'm comparing to this, and I know I see the x squared plus bx, or the x squared minus 8x, and I know I want to complete the square. So basically what I'm going to do is I'm going to take this expression that's under the square root and I'm going to rewrite it. Now, if there was something in front of the x squared, like a 2 or a 4 or a negative 3 or something like that, I would factor out that constant from both of these terms. In order to complete the square, we need a 1 in front of the x squared. Since we already have a 1 in front of the x squared, we don't have to factor anything out, but if there was something there, we would. So then I see the negative 8. That's my b. I'm matching this pattern, x squared plus bx. So b equals negative 8. I'm going to take half of that, that's negative 4, and square it. Negative 4 times negative 4, negative times negative is a positive 16. That's the number that we have to add to complete this square. So I'm going to add that here. And that's going to make that a perfect square. And that's legal. This is going to be equal to the original expression under the radical, as long as I also subtract 16. Adding 16 and then subtracting 16, that's just adding a 0. So I haven't changed the quantity itself. It's still x squared minus 8x, but now it's got a perfect square in it. I've got this perfect square minus 16. So I'll factor this. First times first is x squared, so I've got an x and an x. I need two numbers that multiply to give me a positive 16 that add together to give me a negative 8. 4 times 4 is 16, and negative 4 plus negative 4 is negative 8, so this is going to be a negative 4 and a negative 4, or we'll have x minus 4 squared. Now, a shortcut for that factoring process is to just look at the 16, take the square root of that, you get a 4. That's the number that's going to go here inside the perfect square. And if there's a minus there, this is going to be a minus. And that comes from the fact that if we FOIL this, we're going to get that. So this expression under the radical is exactly equal to this. So I'm going to replace it. I've got x minus 4 out here, all in parentheses, times the square root of this expression, which we rewrote to be this. So I'm just replacing it. Now I ask myself, do I have a rule for that? Well, not in its current form. It doesn't look exactly like one of my rules. But I notice I've got an x minus 4 here and an x minus 4 here. So that's a constant over something times the square root of that something squared minus 16. Isn't that our arc secant rule? Just with a u sub? That often happens whenever we complete the square. So we're going to do a u sub. And remember, whenever you're doing a u substitution, you are looking for an inside function, and you're hoping that after you do the u sub, the integrand will match one of the patterns that we have in our table of rules. And if I let u equal x minus 4, that'll work. So that's my u. du is the derivative of that, which is 1, times dx. So my entire integral can be rewritten this way. I've got 3 over this x minus 4, which we know is a u. So that was our u. And that's an x minus 4 squared, so that's u squared, minus 16. If you want to match that pattern exactly, you could write 16 as 4 squared times dx, or excuse me, times dx, which is equal to du. And now this matches that rule exactly. So I just need to identify a and then apply the rule. So we had a squared equals 4 squared, or a squared equals 16. So a equals the square root of that. It's always the positive square root, so a equals 4. And according to that rule, we're going to have, well, I'd get 1 over a times the arc secant of the absolute value of u over a plus c if I had a 1 in the numerator. But I've got a 3 in the numerator. So if you want, you can factor that out. It's not a necessary step, but for some people, when you're just getting started with integrals, it's helpful to factor out those constants, just to remind yourself that we're going to have a constant times the antiderivative that comes from this rule. Okay, so now I'm going to apply my rule. First I bring my constant down, and then according to my rule, I've got 1 over a, and a was 4, so I'll plug that in, times the arc secant of the absolute value of u over a plus c. So I'll substitute in my u, I'll substitute in a equals 4. And we're not quite done yet. This can be cleaned up a little bit, and of course we need our final answer in terms of x, not u. 3 times 1/4 simplifies to 3/4. And we need to back substitute. U was x minus 4, so you plug that back in. And with the arc secant, we need the absolute value bars. So that's it. That is the technique of completing the square and then doing a u substitution to finish the problem. Now again, you're going to use this technique of completing the square whenever you see an x squared plus bx in the integrand and your basic rules do not apply. And it turns out that a lot of the time when we're doing this, after completing the square, it's going to be one of our inverse trig antiderivatives with the u sub. So that's our first example. Let's do another one. So let's see, I have the integral of 5 over 2x squared plus 4x plus, let's see, I'm trying to make up one that actually works. let's say 20. Now, the farther we get into our techniques for antiderivatives, the more you might wonder about this problem. But at this point, all I have are my basic rules, U substitution, and the 9 techniques at the bottom of my sheet. So I just need to ask myself, go through our checklist, say 1, do the basic rules apply? I go to my sheet, do I have a rule for that? Do I have a rule for anything that looks even remotely like this? Well, I've got an x squared plus a squared in the denominator with a constant in the numerator. Like, that would be an arctan, but this is not exactly like that because of the 4x. So no, my basic rules do not apply. Check that out. And then the next question would be, does U substitution apply? So I look at this and I think about what could a possible U be. Now remember, whenever you're doing U sub, you're looking for parentheses, maybe an expression under a square root, maybe an expression inside an exponential function. You're basically looking for a function inside a function because it's doing the chain rule backwards, basically, when you take this antiderivative. You need to see that composite function or composition of functions, something inside something else, for a U sub to apply. And the only potential U sub that we could have here, or only potential inside function, or U, that we would have here is U being equal to the denominator. And the only way that that would work is if a constant times du was up here somewhere, so that everything up here could be written entirely in terms of U, and then apply a basic rule to that to take our antiderivative. So let's try that. Turns out it doesn't work, but let me show you why. The only choice, the only possible U here, might be U equals the entire denominator. So I might have a 5 over U, maybe some constant times du, and then we would have a rule for that. So then I compute du. So you take the derivative, multiply by dx, and then you ask yourself, do you have this up here as a factor? Do I have a 4x plus 4 dx as a factor? Now don't be tempted to think of that as a 4x plus 4 times an extra 5. It doesn't work that way. Besides, that's in the denominator. I need a 4x plus 4, or a constant times a 4x plus 4 dx in the numerator, and I don't have that. I've just got the 5. So if this was my u, that would be my du, and it's just not going to work. I'm not going to be able to write everything up here in terms of u. So u sub fails. We tried it. We tried the only real possible option. So now we're going to go to our 9 techniques. And because you've already learned about completing the square, you might look at this and say, I'm probably supposed to complete the square because I've got that x squared term and that constant times x squared term. So whenever I see that x squared plus bx, or a constant times x squared plus bx, I'm going to try to complete the square from our 9 techniques. So I'm going to start with the denominator, and I'm going to complete the square and hope that after completing the square, one of my rules will apply. Well, after doing a u sub as well. So I've got 2x squared plus 4x plus 20. And the first thing I want to do is factor out a 2 from both of these first 2 terms. Now, you actually do have a 2 in common to all 3 terms, so in this case it might make sense to just take the 2 out of everything. And that would work just fine. Here's a quick factoring review. I ask myself, 2 times what gives me 2x squared? That's 2x squared. 2 times what will give me the 4x? Well, that's a 2x. And I ask myself, 2 times what gives me the 20? And that's a 10. So now this looks like inside, ignoring the 2, a 1x squared plus bx. And then there's this extra 10 that I really don't need when I complete the square. But I do need to keep track of it. So that's there, and this fits that form. So I'll be able to complete the square from here now. I'm going to bring my 2 down. I'm not doing anything with it. And then I'll have an x squared plus 2x. And I'm going to leave a little space to add something to complete that square. and I'll add the 10 over here. Now remember, whenever we complete the square, we take the number in front of the x after there's a 1 in front of the x squared. We call that b. Take half of that and square it. Of course, 1 squared is 1. You want to add that to complete the square, and then to compensate for adding the 1, we're going to subtract 1. Because if I add 1 and subtract 1, that's basically just adding 0 to the whole thing. And if I'm adding 0 to the whole thing, I'm not changing the quantity at all. So now, after adding this 1, this is a perfect square, which is what we wanted. And then I've just got this extra constant on the outside. So after I've completed the square, I'm going to write that as a perfect square and simplify that. So I've got 2. Not really doing anything with that. I'm going to change from parentheses to brackets because there are so many grouping symbols. And then this is a perfect square. So I need to ask myself, what two numbers multiply to give me a positive 1 that adds a 2? Well, positive 1 and positive 1. So it's going to be x plus 1 times x plus 1, or x plus 1 squared. And then you just simplify that over there. That's just a plus 9. Now remember what this was. We did a bunch of algebra, but this was our original denominator. We took our original denominator, which was this, and we rewrote it this way. So I'm just going to replace this whole thing with this whole thing. And then our hope is that after doing a u sub, one of our basic rules will apply. So I'm going to rewrite my integral. I had a 5 over the denominator, and the denominator can be replaced by that. All right, I'm right here. So say, do I have a rule for that? I do. This 2 is a little bit of an issue, but remember, you've got a 5 over 2 here. That's just a constant. If you want, you can pull that constant out. So I'm going to pull out the 5 over 2, and then I'm left with a 1 in the numerator over the quantity x plus 1 squared plus 9. Now some students are like, wait, what did you do? Remember, when you're multiplying fractions, you can multiply straight across. 5 times 1 is going to give me that 5, and this denominator times that denominator, imagine the whole thing in brackets, that times that gives me that. So this times this really is this, so I've just pulled off the constant, brought that outside of my integral, and now I can think about which rules apply to this. So I'm looking at that. I'm thinking about all of my rules. And the one that it reminds me most of is the Arctan Rule. So you've got a rule on your list that says the integral of a squared, or 1 over a squared plus x squared dx is 1 over a times the arctan of x over a plus c. Now you might say, that doesn't look exactly like that. I don't have an a squared plus x squared. I've got an x plus 1 squared plus 9. But that's just a constant squared, and that's just a function of x squared. So I think that with a u sub, this really does match this form. Notice also that you've got a variable expression squared here, and then you've got the variable expression squared second here. The fact that this is not 9 plus 1 plus x squared, it's not written in the reverse order, doesn't make any difference at all. Whenever you're adding or subtracting, you can add whenever you're adding, you can add in any order that you want. Order doesn't matter. We call that commutativity. Yeah, we can do a u sub from here. All right, so I'm going to ask myself what function is inside another function and makes it match this rule, and it's going to be the x plus 1. The set of parentheses is a big clue. Now you have to remember those parentheses though when you do your factoring up here. Be very, very careful about the parentheses. Without them, it's not exactly the same thing. The quantities aren't the same. So I'm going to let u equal x plus 1, compute du, derivative of x plus 1 is 1, and then we multiply by dx. So everything up here can be written in terms of u. So I've got 5 over 2 times the integral of 1 over u squared plus 9, because that's my u, and then it's squared. I'm adding 9. And dx, that's literally the same thing as du, according to that. So I've got that. Now that is exactly like that. You know, it doesn't matter that there's a u and there's an x. I mean, that's just a dummy variable. It doesn't matter that the 9 is second instead of first. We can add in any order we want. So this matches my Arctan rule. The constant squared is what we're calling a squared. So if I have a constant, in this case it's 9, that's my a squared. Take the square root of that to get a. Square root of 9 is 3. So according to our rule, well, first I bring my 5 over 2 down, then I multiply by 1 over a. And my a is 3. And then I have the arctan of u over a plus c. And a was 3. So we're almost done. Now that coefficient can be cleaned up a bit, and remember, I should be able to take the derivative of this, and after simplification, I should get this back, my integral, or my integrand. This is an antiderivative. The derivative of the result should give me the original function back. This has a u in it. The original function had an x in it, so taking the derivative of this is not going to get me that unless I back substitute. Remember, u is just something that you made up so that it would match the rule so that we could evaluate the antiderivative. So you've got to plug u back in when you're done. Multiply straight across. We've got 5 over 6 times the arctan of u over 3 plus c. And u was x plus 1. So you plug that in, and you're done. Okay. Last one. This is also completing the square problem. Now on the surface you may be very tempted to do a u sub. It looks like a u sub to me. As soon as I see that square root and the function of x under the square root, I'm thinking this is probably a u sub, but it turns out that it's not a u substitution. First of all, our basic rules do not apply. I could write this as 2x minus x squared, all in parentheses, to the negative 1/2 power, bring that up to the numerator, but that's not going to help us. Because I'm subtracting these two terms, that really doesn't get me anywhere. So basic rules don't apply. The next thing I would do is try u sub. So I'd say, let's say if I were to do a u sub on this, u would have to be the inside function, 2x minus x squared. Let's take its derivative. So I get 2x minus, or 2 minus 2x, don't forget your dx, is 2 minus 2x times dx a factor up here anywhere? Or can I multiply this by a constant and get that 7? Absolutely not, I've got this extra x. Now you might be tempted, oh well, I could multiply by an x or do something weird, like something down here. It's in the denominator, that's not going to work. I need a constant times this in the numerator, and I don't have it. All I have is this 7 and dx. So u sub fails. We tried basic rules, they didn't apply. We tried u sub doesn't apply. And you don't have to do this every time. You can do that in your head if you want to, but you do need to check basic rules, then u sub, And then if none of those work, then you go to your 9 techniques. And then I notice, I've got an x squared term and an x term. This is a good candidate for completing the square. So we'll say, since we see an x squared plus bx, we're just going to try completing the square. And it turns out that that works. Oops. All right. So again, I'm going to start by taking that ax squared plus bx, like the expression involving that x squared and the bx, and rewriting it. Now first I want to write it in a different order. We usually like to have our x squared term first. Remember, you can add in any order you want. So that's 2x plus negative x squared. So I could make that negative x squared plus 2x. Totally legal. And this is the same as that. So that's under the radical. Now in order to do completing the square, I need a 1 in front of the x squared, not a negative 1. So I can factor out that negative 1 from this term and this term. Negative 1 times x squared gives me my first term. Negative 1 times times a negative 2x. Negative times negative gives me a positive 2x. And this is what I'm going to complete. I'm going to add something to that to make it a perfect square. And I'm going to leave a bunch of space so that I can add something and then subtract to compensate. So I'm ready. Identify my b, take half of that, square it. Negative 1 times negative 1 is a positive 1. Add that 1 to complete the square. And then remember, if you're adding 1, to compensate for adding 1, you have to subtract 1. So now this is a perfect square, and I'm subtracting 1 from that. So I've got negative 1 times, I'm going to use brackets now, this perfect square. I ask myself, what times what will give me a positive 1? Well, a 1. And I need that number plus that number to be negative 2, so it's going to be a negative 1. Negative 1 plus negative 1 is negative 2, and negative 1 squared is 1. Another quick way to always get this is to just look at the b over 2. That negative 1, that's what's going to go right there. Or you could just factor the traditional way, and you'll just see that that's an x minus 1 times x minus 1. So you've got x minus 1 squared. That negative 1 over here, you just want to bring it down. Now don't forget about this negative 1. This negative 1 can distribute through the parentheses. So I have a negative 1, or excuse me, negative 1 distribute through the brackets. Negative 1 times that quantity is just a minus x minus 1 squared. And a negative 1 times a negative 1 is a positive 1. Now because we usually like to have a positive term first, I'm going to write the 1 in front. So I've got 1 minus x minus 1 squared. This is a new way of writing that expression under the radical. So I can replace all of this with this. And that's exactly what I'm going to do. And then our hope is that if I do that, a basic rule will apply. No guarantees, but we're hoping it'll work out. So I replace this with this. And the question is, does that match any of our rules? Now, if you're not sure, you should go back down through your list, and you'll see there is a rule that looks something like that. And it's the Arcsine Rule. I've got a rule for 1 over the square root of a squared minus x squared dx. Now you have to be very careful with this. This is subtraction, so the order does matter. That's got to be a constant squared, or just a constant really. You know, it doesn't matter if it's an irrational number when we take the square root. Just got a constant here, minus your variable squared. If this fits the form exactly, then turns out we get an arcsine of the not absolute value, arcsine of x over a, and don't forget to add your c. And again, all of those rules were derived way back in Calculus 1. So you might want to watch those old videos or crack open your book and check it out, that this is the antiderivative of that. So we're here, and it matches almost, but I don't have an x. I've got an x minus 1. That's okay. I can do a u sub. If I do a u sub, it's going to match that form. It's going to use a u instead of an x, but that's okay. It's just a dummy variable. So we can move on from here. So I'm going to let u equal x minus 1. Compute du. And then our hope is, after rewriting this guy, that rule will apply. We've got 7 over the square root of 1 minus, that's my u. Don't forget to square it. A lot of people just write 1 minus u, but then they'd be incorrect because that's not just an x minus 1, it's an x minus 1 squared. So I need to have that square here. And then dx turns out to be exactly the same as du, so put that over here. Now I'm looking at this and I'm looking at that, and yes, that fits the form exactly. I've got a u instead of an x, no big deal. A squared is 1, and that's 7, also not a big deal, I can factor it out. I don't know why I put a little line through that one and not that one. I think it's pretty. I'm going to do that from now on. So we're going to factor out the 7, just to make it look a little bit more like our rule. You don't have to do that, as long as you remember to bring down the 7 when you antidifferentiate. Now we're here. In order to apply this rule, I need to figure out what a is. So identify a squared. A squared's 1. Take the square root. Of course, the square root of 1 is 1. And so we get, according to our rule, 7 times the antiderivative of this, which is the arcsine of u over a plus c. Substitute in your u, substitute in your a, which happens to be 1, so I don't really need it. And then again, we want to simplify this. I don't need to divide by 1, it's just a u. And then I need to back substitute. U is the same as x minus 1, so I'm going to plug that in. And that's that. Now you might be saying, wait a minute, are you sure? Are you sure that if I take the derivative of this, I get that back? And we can check it out. So let's check. This is the only one we would be checking. And again, you want to remember, if you want to check this, you're going to have to recall this rule way back in Calc 1. Remember, the derivative of the arcsine of x is 1 over the square root of 1 minus x squared. And if there's something other than an x inside, we're going to have to use the chain rule. So with that in mind, I'm going to take the derivative of this answer. This is the derivative of what's supposed to be an antiderivative. I should get the function back. Okay. So I've got a constant times a function. The derivative of a constant times a function is that constant times the derivative of the function. Now the derivative of arcsine of this, well, that's my inside function. According to the chain rule, I first take the derivative of the outside. The derivative of arcsine of something is 1 over the square root of 1 minus that something squared. Or the derivative of arcsine of a function is 1 over the square root of 1 minus the function squared. Plug the function back in. And then by the chain rule, we multiply by the derivative of the inside. And that's just a 1. And then, of course, we're taking the derivative of a sum. It's the sum of the derivatives. What's the derivative of a constant? 0. That's right. It's not that constant times x. That's the antiderivative. Okay, so we're here. Is that the original integrand? Not exactly. Maybe if we simplify it, it will be. So multiply straight across. That's a 7 over an implied 1. And that 1 times that 1 up there is also just a 1. So 7 times 1 times 1, so that's 7. All divided by this. And you might say, it still doesn't look like the original function, but that's actually what we got when we completed the square. That's actually what we got right there. If you want to be sure, though, multiply it out. Do a little foiling. First times first is x squared. Outer times outer is negative x. Inner times inner is another negative x. That's negative 2x. Last times last is plus 1, excuse me. And so we've got 7 over the square root of 1 minus x squared minus a negative 2x. Plus 2x minus 1. And the 1 minus 1, those will reduce. And I'm running out of space. You eventually get this, and we can add and subtract in any order we want. So we could put the 2x first. And I believe that's our original integrand. So we know it works. That's completing the square.